in the last session, we started talking about tunneling, if you might remember, and it was like this crazy quantum effect that happens, especially in nanoscale devices. And I kind of explained the process, the phenomena, and then we tried to do some simple maths, but then we ran out of time, so I stopped, right? And I know it's been a while, so I'm going to give you a very high-level quick overview of what tunneling is. So imagine you have a barrier, an energy barrier. And when I say barrier, even if I don't specify, the default would be energy barrier. So imagine you have a particle, an electron. It's trying to get towards the barrier. For the time being, imagine this is like a small rock, and this is a mountain. If you throw a rock at a mountain, as you know, using our common sense, it's probably going to just stay within this region, unless you provide it enough energy to take it up and then throw it on top of the barrier. Now, let's get back to the electron argument. If you think of it like a y-axis plot where energy is plotted in the y direction, and if an electron is here, it shows that the electron energy is lower. If the electron is here at point B, A versus B, the energy is higher at point B, all right? Now, if the electron has higher energy than the barrier, the electron can just pass over on top of it. No barrier. The barrier will have absolutely no effect. Does that make sense? The only time it will really act as a barrier is if the electron energy, the energy of the electron, is less than the potential energy, and this potential is typically marked as V0. So if the energy of an electron is less than the potential energy that you are imposing, so then the electron will be kind of stuck here, and it will be difficult for the electron to go to the other region. And I told you, according to quantum mechanics, and it's simply based on math, and many times you'll be surprised to see how many of these concepts came into being through mathematics, just mathematics. And then apparently people started doing some experiments, and they realized that they do actually exist. All right, so that's how it came into being. So simply by going through some quantum mechanics, we find a solution where it appears that, I think we did it in the last slide here, that in all three regions, there will be non-zero probability of finding electron. So you can potentially find electron here or here or here. So that's what was the surprising conclusion from some maths, quantum mechanical maths. So sure, okay, but what does that really represent? It shows that if you throw an electron at a barrier, the electron can potentially tunnel through the barrier and get to the other side. That's the take-home message. Electrons are capable of tunneling. But who determines the probability of tunneling? This equation was the key. It's transmission probability or probability of tunneling, however you want to put it. The higher the probability of tunneling is, the more tunneling will actually occur. The lower the probability, basically it's unlikely to happen. And we noticed that the tunneling probability was a function of the thickness of the barrier. If the barrier is thicker, there will be less tunneling. And also it was a function of the barrier height. The higher the barrier, there will be some relationship with tunneling, but it is not really as straightforward as thickness. So the easiest tuning knob for engineers to deal with, to control tunneling, is this thickness. I don't think I gave you an example, but maybe I should. I guess we were running out of time, so I wanted to skip taking any tangents. But I have the luxury to spend a few minutes giving you an example. Let me show you. Imagine you have a sample which is really, really, really small, nanoscale. I mean, when I say small, I typically mean nanoscale. So imagine the surface of that looks like this, really rough. You want to find a high definition image in nanoscale and figure out how the topology looks like, all right? One potential way to do so, which people have been using now, is to use tunneling. And here is how it works. You have an electron gun, and I'm making it extremely simple, as you can imagine. So these are all electrons, and we are going to keep it at the same level here. We are going to push it horizontally, both left and right. And actually it's in 2D, but it's okay. For the sake of it, let's just consider this to be a one-dimensional direction. All right. So when you move it to the left and right and keep shooting electrons. See, the total barrier, imagine this thickness is fixed. This is, say, T1. And there will be some additional thickness because of the topology, you see? In different sections, there will be effective thickness. Does that make sense to you? So, for example, when this guy comes to this region, maybe, comes to this, this region, and tries to throw electron at this material, all on a sudden, the total thickness observed will be this much. Let's put it as, say, T2. And here in this region, the total thickness would be T1. Do you see that? Does that make sense to you guys? Is that clear? Okay. So apparently, as this probe moves to the left and right and keep throwing electrons, there will be a probability of getting electrons tunnel through this sample and get out to the other side. Maybe here you have a sensor. You have an electron sensor, and it's sensing how many electrons are there. Okay, so the thicker the region is, the less electrons you'll get because the probability of tunneling will be lower. You see, and it's extremely sensitive to the thickness. Why? Remember that relationship, anything that is within an exponent, and we always use this term, there has been an exponential increase in crime rate, right? Don't you? So exponential always represents something dramatic, right? So since this thickness is inside the exponent, it really represents that there will be a lot of change because of thickness, simply because of thickness. All right? Does that make sense to you guys? All right. Now, based on how many electrons you get and sensing that electron, you can easily calculate and figure out and plot the thickness essentially. And the thickness will give you the topology that you are trying to see. That's how we often do microscope using electrons, electron tunneling. See, there is a direct application. You might wonder, how do we know tunneling is true? Because we are using it to make images. All right. Anyways, so let's go back to the slide where we stopped in the last class. So let's try to, as engineers, let's try to use this equation and find some numbers out of it. So the problem states, consider an electron with an energy of 2 electron volt. And the reason for having this type of simple math problem is to help you, take any useful information and plug them in the equation so that you get something useful out of it. So you know the energy of the electron that is being thrown at a potential barrier with V0, which is the potential energy, 20 electron volt. And notice we always measure measure energy in electron volts, right? For semiconductor stuff, typically. All right. Now, and a width of 3 angstrom. 3 angstrom. All right. Let's see. Calculate the probability of electron tunneling through the potential barrier. So let's try to put in those numbers. This is the equation that represents the tunneling probability. And what is that? E is the energy of electron. Do you know the value of E? See, it's given 2 electron volts. So you could just put them here. Do you know the barrier height? 20 electron volt. So you can also put that in here. Any problems so far, folks? All right. Width of the barrier, which is this thing. And by the way, notice this is basically A. So in the equation that you have, A represents the barrier thickness, which is 3 angstrom. Any problems so far? Very simple. And similarly, as we discussed in the last slide, you might remember here, in 2 regions, we had 2 wave numbers. K2 is the one that we really care about because that's within the barrier. And K2 had an expression like this, which is a function of the energy of the electron and the energy of the barrier that we are dealing with. So you already know all those numbers. Just put them in and plug it in here, and you get the transmission probability. And by the way, just by looking at this transmission probability, you can figure out which one is more probable, which one is less probable, and you can design accordingly. And I just gave you a direct example, engineering example of how the transmission probability can be calculated and back calculated to get the thickness. Are you guys all with me so far? All right. And I think I give you another example using MOSFET, where tunneling plays a role in determining the gate thickness. We'll get back to it towards the very end of this course when we end with MOSFET lecture, and you'll see how impactful these concepts can be. And I already told you that none of these slides that you see here, they're meaningless. All of them are chosen very carefully so that at some point they will answer some questions. Okay, this is the last slide for this particular lecture, where I tried to project the simple math exercise to 3D. So in the previous examples where if I just go back a few slides, where we started with Schrodinger's equation and did some math and came up with some concept. It all started with this simple stuff, which I expected a question on, but never received that question. The question could have been, oh, hold on. Why are you always just dealing with X? What's wrong with Y and Z? Where is Y and Z? Right? Basically, I simplified the math for our sake. It's not just me. Even in textbooks, they simplify the math so that you can do things analytically. Otherwise, it will be just math and nobody will listen to anything, right? So it's a simple approximation to consider a one-dimensional Schrodinger's equation. But in 3D, you have X, Y, and Z. So the equation becomes more complicated and the solution will have more maths involved, obviously. But typically, for many situations involving 3D structures, we don't always deal with X, Y, Z. We deal with spherical coordinate system that involves R, theta, phi, just to let you know. And when you're dealing with an atom, it's not a 1D object, it's a 3-dimensional object. So you have to deal with spherical coordinate. And these details are always there in some textbooks in case you are ever interested, or if you take any quantum mechanics course, they will make you do it, do this, math stuff. So apparently, this is the form. There are ways to represent 3D using spherical coordinates. So if you basically use this math and go through the solutions, eventually you will arrive at a conclusion where you have 3 quantum number playing roles within an atom. And let me take a step back. How many of you remember the situation where an electron was trapped in a quantum well? What was the take-home message? When an electron is trapped, its energy becomes quantized. Remember that take-home message? It's been a while, I know, so it's not immediately clear to you, maybe. But that was a very big conclusion, that the moment you trap an electron somewhere, it can no longer have any energy at once. Its energy becomes quantized and predetermined. Okay. An atom is more like a 3-dimensional confinement that traps electrons. So electrons are trapped in 3 dimensions. So just notice that you have 3-dimensional confinement, and therefore you have 3 different quantum numbers. So it's as if the electrons are triple quantized. They are quantized with 3 different numbers. Making sense? And these all come as maths, like pure maths. Many of these were actually done by mathematicians who don't care about physics, for example. So they basically just take math and solve it and say they come up with some solution. Some of these appear to be too crazy to be true, and people realize that there must be some mistake. We cannot figure out the mistake now, but there is a mistake. But few decades down the line, people realize that was not a mistake, that was reality. Okay. Anyways, so we'll get back to these quantum numbers in the next lecture. The very slide of next lecture, we'll start with this one: primary quantum number, angular quantum number, magnetic quantum number. As you've seen, I'm not going through the maths. Obviously, this is the purpose. So I'm not going to show you how these numbers arrive, but I'm going to show you how to calculate these numbers. Another take-home message from this slide is that after you go through the math, you end up with an equation that shows the energy of electrons trapped in an atom will be quantized, obviously, as you can imagine. And this is how it is related. N is an integer. So by putting in n equals 1, n equals 2, n equals 3, and so on, you can get different energy levels that electrons can get within an atom. Does that make sense? So one more important take-home message, and all of these points are there written here. And these texts are typically taken from the textbook. And I told you that you don't necessarily need to get the textbook, because if you keep reading through them, you will never know how much to read and how much is necessary for you to understand the devices, apparently, because there is too much. And I don't want you to be demotivated just by reading too much and then, oh, no, it's not for me. All right. So I just want to give you a sense that even if you stay superficial, you can get to the point where you can start making contribution. So another take-home message is simply by math, and I'm trying to stress this over and over again, we arrive at a situation where the energy looks negative. So apparently, the energy of an electron in an atom is negative. What does that mean? So let me just go back here in this like whiteboard. Imagine if you had a well like this, where you had V0 energy here and 0 here, and an electron is stuck. This is basically a quantum well, don't you think? Basically a quantum well. Now, what if energy is 0 everywhere else? 0 everywhere else. And negative here. So some sort of negative energy. Isn't that exactly the same thing? It's just a mathematical, representation. That's all. Basically, it represents the same thing. But I figured that you might be confused with the negative sign and you might have some questions. And even the textbook mentioned that. All it represents is just, it's a quantum well, that's all. Because we started with 0 here. If this is 0, this will be negative. So similarly, instead of V0, if you treat this to be 0, this will be negative V0. Don't you think? All right. So no need to be confused about negative energy or whatnot. So move to the next slide. This is the last slide where I wanted to show where we are headed. So remember the quantum well argument that we discussed? That quantum well will come into handy when we discuss energy in an atom. So if you start putting in numbers, n equals 1, n equals 2, n equals 3, you can get the energy numbers. And if you start plotting them, this is how they look. E1, E2, E3, E4. Does that make sense to you guys? All right. And basically, this is I haven't explained what this thing is. So when we draw quantum well this way, this is a very simplistic approximation. There is no well which is absolutely sharp, right? Everything is gradual. So as you imagine, this is your nucleus. As you come closer to the nucleus, electrons become more and more stuck. The farther out you go, they become more relaxed. Okay, so there is a gradual decrease in energy as you move closer to the nucleus for electrons. Am I making sense, folks? Can I put it in a different way so that you can remember? So anything that you like to do naturally will basically have a reduced energy aspect with it. So electrons are negative charge particles, and nucleus is positively charged, say. So will the electrons like to go towards nucleus or not? What do you think? Positive and negative, they should attract each other. So the electrons should be fine going towards the nucleus. They will like it, oh, sure. I mean, does that make sense? So the closer the electrons get to the nucleus, the less they will resist. And so the least energy they will have. I know there are many other forces at play, but just as a very simplistic approximation, and to help you understand the shape of this graph. And this, again, this comes mathematically. If you solve the equation, it comes mathematically. But apparently, even to understand this, the closer you get, the less energy you will have overall. Same thing applies here. This is in 3D. So so what happens here? It's not just here and there, it's 3D. Just visualize this like a vortex, like a 3D vortex, where everything is kind of like a black hole in here. Instead of black hole, visualize this like a nucleus. So the closer you get to the nucleus, the sharper the slope becomes, and the electrons are trapped. It's not easy for the electron to get out. And within that vortex, towards the nucleus, there are different levels of energy. The moment the electrons get trapped, the nucleus will ascend, hey, go to this shell, that shell, this shell, that shell. So there are predefined energy levels where the electrons will get stuck, and they cannot do anything about it. That's where quantum mechanics dictates the rule. Make sense? Okay. Now, again, this is what we get if we basically go through the math and solve this equation, and we just arrive at this solution. And these levels are dictated by this equation right here. Simple. Now, I just want to show you in a crystal that we care about in material science or anything else, we deal with crystals. We don't deal with individual atoms. There are multiple atoms side by side. They come together, they interact with each other. Notice all I tried to do here is to show you one atom, second atom, third atom, fourth atom. So basically you have multiple atoms in a crystal. they are interacting with each other. So what happens with this interaction? Imagine. So this and the other atom, they will interact with each other and their potential will merge and form an equivalent situation here. Do you see that? Geometrically, just consider the math again. These are coming from simple math. If you plot them together and add them together, it will show up as something like this. Yes, these two graphs will lead to a shape like this, a dome-shaped graph. That's all. Now, apparently, the electrons can be stuck here and there is a barrier. Stuck here and there is a barrier, and so on. So electrons are stuck in different places in the crystal and there will be barrier. Now, can you visualize this as low energy, high energy? In a simplistic form, a quantum well, like a well where the electrons get stuck, as we discussed in the few slides back, right? That was a simplistic approximation just to make a point. Obviously, if the energy gets stuck here in this type of a well, it will also be stuck in a well which is like more gradual and more practical, obviously. Take-home message is just the same. All right. So we'll get back to it in chronic penny model, which is in the next slide. Next lecture. So obviously, let's get started with that today. Lecture 5. Lecture 5. Folks, just to take a moment. Do you guys have any questions? Yes. I think I did. Yeah. There is, okay. So what I will do is maybe I will post it after the class, if that is okay. And anyways, there is recording, so you can take a look at it. I know what happened, I guess. So once I upload, I'll have to check and make it public. So typically many of these are like hidden. I think I have all the lectures uploaded, but I forgot to, make it public. So thank you for pointing it out. All right. So again, just to reiterate the fact, all of these are concept heavy and lecture heavy. You're seeing less concrete material and more talks. But I just keep telling you to be patient and please pay attention, because these are like the bare minimum that you need to have in your head to have any kind of educated discussion with modern day semiconductor scientist or engineer. So if you work for any company which actually deals with the cutting edge, not the legacy, the chip makers that makes chips for printers or toys, for example, because they also have chips, I told you, right? But if you deal with something which is more cutting edge, then there is no exception, and you actually need more. But I want to prepare you with the absolute bare minimum at least, so that you can learn more when you get there. Anyways, why am I telling you this? Because there will be more crazy stuff coming in here. And there is a place where I mark with begin and end, that within that zone, you could just forget it after the class if you want to. You don't have to even remember this. But I still want to show you, because as a student, when I was a student like you, it was really, really problematic for me to not have any idea how that thing came into being. So I just want to show you there is a path, there is few math that you can do, some references are available as well. And in fact, the textbooks that we have, they also show the detailed maths in some places. So you could go to the textbook and see the detailed math. Anyways, so the next concept that we'll talk about is Pauli's exclusion principle. Let me just state that in a very simplistic way, and then you can read it later on or read the textbook. The simple fact is, imagine a system. And when I say system, an atom is a system, a molecule is a system, as a crystal is also a system. So in any system where multiple electrons are interacting with each other, no two electrons can have the exact same quantum state. Okay, and let me kind of clarify this. What do we mean by quantum state? And that's what I'm going to explain using this chart. Ready for it? Remember, in a few slides back, I showed you if you solve the Schrodinger's equation for an atom, you get 3 different quantum numbers: N, M, L. Okay? Just told you, right? By the way, there is a 4th quantum number, which we didn't talk about there, which is a spin quantum number. So apparently, there are 4 numbers that identify an electron. It's kind of like a tag. Imagine in a 3-dimensional coordinate system, if you have a point, to identify that point, you need 3 information: X, Y, and Z. So X, Y, and Z coordinate form the coordinate of the point, which we could use to identify a specific point. Similarly, in a quantum system, there are 4 quantum numbers that we use to identify each and every particle, like electron. And Pauli's exclusion principle tells you that this tag is unique, as simple as that. This tag is unique. The tag for one electron is unique. There cannot be 2 electrons with exactly the same quantum tag. Am I making sense? So let's try to first learn to calculate the tag. Hydrogen, helium, lithium, beryllium, as you see, we're going to the periodic table, chemistry. So what matters is how many electrons you have. That means the more electrons you have, more candidates in the system. So you have to assign them specific tags. If you have 8 electrons, they should have 8 unique quantum tags. 8 unique quantum tags, okay? Let's see. Imagine you start with 1 electron. So 1s1. So apparently the primary quantum number is 1. And basically the primary quantum number represents the shell. Remember that E1, E2, E3 that we basically try to plot? They are like the primary levels. And within those primary levels, there are secondary and tertiary states. And that's what we are going to talk about. So without going into too much chemistry or other stuff, for the first, if you see 1 here, that represents E1, like first level of energy. So your N primary quantum number will be 1. So just take a look at the electron distribution from chemistry and try to understand the primary quantum number. So you have 1 here, your primary quantum number is 1. In, say, beryllium, for example, you have both 1 and 2. So your primary quantum number maximum is 2, N equals 2. And by the way, why am I just looking at 2? Why not 1 as well? I forgot to tell you that. And I hope you remember it from chemistry. For any atom, the most impactful electrons are those that are in the outermost shell, because they take care of all the chemistry, they take care of all the interactions. So whatever is the most outermost, that's the only thing that we care about. So for hydrogen, we have 1 shell, so there is no outermost or innermost. It's just 1. So N equals 1. For this atom, beryllium, 2 is the outermost, obviously. So our primary quantum number is 2. For, let's see, okay, all of these are tiny. So 2 would be the max we go. But typically it could be 3, 4, 5, whatever, right? So let's see. Secondary, other quantum number that you get will be starting from 0 all the way to N minus 1. Remember that. And I told you, it all comes from pure math. Nobody cares, like pure trigonometry, for example. Anyways, so if you start with 1, N equals 1, L could only be 0. You see that? Okay, let's start with N equal 2. If you start with N equal 2, L could be 0 and 1. Can it be anything else? I just told you it can be starting from 0 all the way to N minus 1. What is N minus 1? 1. So that's it. If you get an atom where you have a third shell, N equals 3, what could be L? L could be 0, 1, and 2. Not 3, because it has to be up to N minus 1. Does that make sense to you? I mean, you just have to know how to calculate this. And why am I telling you this? Let's take a look at this one in this section. See, all of them end with 2. So their primary quantum number is basically 2. So for L, you can have 0 and 1. So you can either have 0 or you can either have 1. So that's what this chart shows you, that for the same primary quantum number, I meant to just have this too. For the same primary quantum number, you can have 2 different possible L's. And for every L, don't give up. I know I sound a little bit crazy, like, okay, 1, 2, 3, 4, 5, 6. I'm going to get to the point, honestly, but there is no easy way to skip this. Honestly, if I exclude Pauli exclusion principle, you'll completely miss out on the fundamental reason why semiconductor exists. See how profound this simple, like seemingly irrelevant concept, like, okay, 1, 2, 3, 4, N minus 1 will lead to And that's how science works. Something simple and stupid leads to a dramatically new direction. Okay, so unfortunately, within this lecture, you will see how Pauli's exclusion principle determines the existence of semiconductors. I mean, the simple reason why silicon is a semiconductor is because Pauli's exclusion principle applies. Now let's pay some attention there. Okay. All right. So I just want to show you how M can be calculated. M will be, this is another quantum number. It starts from negative L, goes through 0 all the way to positive L. Okay. Starting from negative L, going through 0 all the way to negative. So let me just take some random example here. Imagine your N equals 3. What could be L? Please tell me. 0, 1, 2. As simple as that. Let's not get confused. Now, for every L, you have multiple M. So just to make that point, for every N, you could have 0, 1, and 2 for this one. Now, for every L, M could be starting from negative L to positive L. So obviously, for 0, you only have 0. Done. Just 1. But for 1, you could have -1, 0, I meant to write M here, or +1. You see that, folks? Let's do for 2. This will be clear. For 2, L equals 2, what could be M? Starting from -2, -1, 0, 1, 2. Done. So starting from -L, 2 all the way to +L. That's how M would be. I'll make a point from this slide. Okay? Take a look. I'm going to make coordinates or tags for every principal quantum number. Can I say 3, 0, 0? This is a tag. This is a unique tag. Let's do something here. And let me just change the color. Here in this route. So for N equals 3, I could also have L equals 2. And for 2, I could have -2 as M. It's just one tag. But there could be multiple other unique tags in the same channel, same branch. Does that make sense to you, folks? So within the first shell, maybe if N equals 1, you have a few quantum states available. You can take this tag, take this tag. Like you can have few tags. When you are out of tags, you can no longer accommodate electrons. You see what I mean? So imagine this is N equals 3 represents the third energy level. So at the third energy level, you have a finite number of available tags. That's why we say we could only, accommodate X amount of electrons in a certain energy level. Do you remember that from chemistry? You cannot just randomly, all of my electrons will go to second shell. No, you cannot have that. Who dictates that? This Pauli's exclusion principle. Okay, so they distribute the electron throughout the atom based on this. All right. One thing, the reason why I didn't close this is because there is one more quantum number which is not as obvious, which doesn't, in terms it's more simple. It can only have two values, +12 and -12. These are called spin quantum numbers. So for every tag, there will be a +12 and there will be 300 -12. For every tag that you create with M, N, L, and M, there will be a +12 and -12 version. Am I making sense? They have to, they're there because, because of the nature of the electrons. Remember, the name suggests spin. That doesn't, oftentimes people mis-explain this in a way that electrons are spinning this way and the other way. This way is +12, the other way is -12. Electrons don't really spin. They're not particles, essentially, as you can know right now, right? So this is a classical analog. This is how people used to visualize stuff, but that's not the real reason. Okay, I don't want to get into that mess right now. But I hope you see from this slide that there are specific tags that you can create with 4 numbers, not 3. I started with 3 because they were kind of related to each other, but then you put in +of and -of to every tag. So the number increases. You basically double the number, but still it's not infinite. You have a finite number of tags. So you can only accommodate a few electrons. And by the way, that's what you see here, +of, -of. For everything, you have +of, -of. All right, now let's move to the next slide, which will show you a more realistic situation. Folks, ready for it? Again, I'm going to skip a lot of math here. I'm just going to show you the result for this one. If you calculate the probability distribution in an atom, what do I mean by probability distribution? The probability of finding an electron at a point in an atom. The probability of finding an electron at a point in an atom. And by the way, I'm going to use this term, radial probability density function. It's not mentioned here, but just remember that it's radial, meaning it's across the radius. So we are using spherical coordinate system. In a sphere, any direction across the radius should be identical, don't you think? So we are looking across the radius in any direction outside. So imagine this is your nucleus. This is where the nucleus is. So you're looking at, starting from the nucleus, looking outside, and see how probable it is for you to find an electron across that radius, along that radius. Does that make sense, folks? Okay, so that's the radial probability density function. So basically, you see, just by math, the probability increases somewhere and then it decreases again. What it represents? It represents it's more probable for you to find an electron that much away from the nucleus, don't you think? In a classical sense, honestly, in a classical sense, when you draw stuff, imagine this is the nucleus, we would have just drawn this. This is electron, this is your A0, which is the atomic radius. Basically, that's how far your energy shell is. That's how we typically used to represent in classical sense. But practically, this represents the same thing. So this is as if this is your nucleus, this is where the electron is, because it's more probable for you to find the electron there. It's more probable. But that doesn't mean it cannot be found anywhere else. Are you guys all with me so far? Okay. All right. Let's see. Sure. I'm trying to come to the point here. So this is for one atom. You see, the farther out you go from the nucleus, the more difficult it is, or more or less probable it is for you to find an electron. Electrons find a zone where they're most comfortable. And by the way, something wrong happens when you come closer as well. You see? I mean, typically this is a question, but okay, what? Positive charge, negative charge. Why can't they just lump together? Then nothing will exist, right? All the electrons will be in the nucleus and there will be nothing, essentially. You guys know about strong nuclear force, weak nuclear force, and all those good stuff, right? They don't play a real involved role in our understanding of semiconductors, so I'm kind of skipping that part. But in case you had that question, those are the reasons. But apparently, there is a specific distance where electrons are most probably found. Now, these two graphs show you what happens when two atoms come closer to each other, like one atom, the other atom. So they are coming closer to each other from two directions. And that's basically how crystals work. Atoms come closer to each other and form crystal. And we are heading to crystals all the time because that's how the materials work. So apparently, as you see, there will be a zone where the probability functions will overlap. You see that, folks? I mean, if I draw the probability function, what did I do? Sorry. If I draw the probability function for one atom and the probability function for the other atom, just flipped, right? Just flip, that's all. Essentially, there will be a zone where it's probable to find both electrons. Electrons for the left one, electrons for the right one. They can overlap. The probability functions of two electrons can overlap. Notice that? And that's a problem. You know why? Because if for some reason they overlap, are they going to have the same quantum tag? Notice, in an atom, when it was independent, and another atom, sorry, I meant to say, in one atom that was independent, another atom that was independent, it's fine as long this electron 2, electron 1, they can have the same tag. You know why? Because they are not related. They are not part of one system. This is system 1, an atom floating somewhere. System 2, atom floating somewhere else. They are not correlated. So they can have the exact same tag. But the moment these atoms come together and they start interacting, meaning these two overlap, that moment, they need to find ways to identify themselves. I am so-and-so electron, that guy is so-and-so electron, despite them having the same tag before. For example, if two person come to the same class with the same name, say Adam, both Adams, right? I would have to call the Adam 1 and Adam 2 similarly. So exactly the same situation, otherwise we'll be running into issues. So similarly, using Pauli's exclusion principle, we'll have to find different tags. It's not just we have to find, the universe finds different quantum tags for the electrons when they come together and start interacting. And then one quantum state will split into two. All on a sudden, one quantum state will spontaneously create two quantum states to accommodate both electrons. They're close to each other, very close to each other. They're not like, oh, shell 1, shell 2. No, not that far out. They're very close to each other, but they will still be different in energy. One of them will have slightly less energy, the other one will have slightly more energy. So they will decide, okay, you take less energy, I'll take more energy, or whatever. Making sense? So somehow there will be splitting. And by the way, this graph now is becoming more and more involved, this concept. So this is energy, electron energy in a crystal. Or forget about crystal. Like, for the time being, let's think of an atom. And this is interatomic distance. Interatomic distance, meaning that, let me show you. So this is an atom, this is an atom. This is the interatomic distance. All right, the distance between two atoms. Now, even before we see the graph, let's try to talk about it qualitatively. What happens when two atoms come closer to each other? Will they interact more or less? Will there be more chances of interaction or not? So when I reduce the interatomic distance, they will interact with each other. And the moment they start interacting, what will happen? The quantum states will go crazy and they will start splitting. It's not just for one state, every state. So, oh, there is a 1, 2, 1, 2 and 3, 2, 3, 2. Both of these states will split into, don't you think? Does that make sense, folks? I just showed you there are different tags, many tags, not just one. But every tag, and by the way, we are looking at the same atom. See, if it is silicon, the other one is also silicon because we are looking at a crystal. So they have the exact same tag. So if there is an X1 electron, there is an X1 electron on the other side as well. So they have the same tag. So the moment they come closer to each other, they start interacting and all those tags will start splitting in two. And maybe more. Why more? Why more? I'm just telling you two atoms. In a crystal, will you just have two atoms here? You have another atom here. You have another atom here, another atom here. All of them will start interacting with each other. So every quantum state will keep splitting into multiple. Do you see? Does that make sense, folks? You see how crystal structure has a lot of role to play? Like cubic, simple cubic, body-centered cubic, face-centered cubic. They determine how many atoms will be close to each other. The neighboring atom, how many neighboring atoms will be there? Now, tell me one thing. If you have just two atoms, when they come closer to each other, start interacting, every quantum state will be split in two. If there are 4, 1, 2, 3, 4, all coming from 4 different directions, then every quantum state will be split in 5 technically. Does that make sense so far? No? Didn't make sense. Why? Let me just take a step back. Okay. Imagine you had two atoms, atom 1 and atom 2, and they came closer to each other. To accommodate their electrons, which are supposed to be identical essentially, you have to have two tags for every tag before. So you have to have, if you have tag 1, now you have tag 1A and tag 1B, just to accommodate both of them. Now, if you have another electron, say another atom, A3, now you have 3 tags. So now you also need tag 1C to tag all of the electrons. So the more atoms you bring in, the more splitting will occur. Does that make sense? So you see, so the number of atom, distribution of atom in a crystal directly impacts the quantumness of the system. How many quantum states will be there? The quantum physics behaves accordingly. Based on who? Pauli's exclusion principle. Am I making sense so far, folks? And I'm getting there to the silicon stuff. Now, you see, the closer the atoms get, the more splitting will occur. If they move farther out, there will be less interaction and less chances of splitting. So that's what you see exactly here. Interatomic distance. If the interatomic distance reduces, you notice there was just one energy level, but that energy level splits into smaller and smaller levels to accommodate electrons. They distribute the electrons. Despite them being the exact same tag previously, now they're going to be distributed into sub shells. I should probably use it, or I mean, whatever you want to call it, but sub quantum states. Are you guys all with me so far? So this is called a band, an energy band. Energy band. Okay. So one energy level splits into bands of energy. Let's move to the next one. Okay. Now it's getting more complicated. You are still looking at an atom. You know, in the previous picture, you only looked at the last shell, just the last shell. We didn't look at the shells inside the atom. So there could be shell 1, shell 2, shell 3. Am I making sense, folks? Some atoms, like hydrogen, only has one shell, just one electron. Some atoms, like silicon, will have 2 shells. Some atoms, like, I don't know, iron, will have 3 shells, and so on. So there will be multiple shells, like depending on the main quantum number. So far, we just dealt with the last one because that's the most relevant. That's what determines everything. But in practice, and all this text will explain what I'm just going to tell you now. Can anybody take a look at it and see an interesting trend that you see? What is interesting about this section? What do you see? First of all of the levels are splitting. It's not just the last level. It's also the first level. It's also the, the minimum level. That's also splitting. All the levels are splitting. But what is different between these levels? Splitting. Can anybody notice that? Thank you so much. Yes. So apparently, by the way, in this direction, which is less interatomic distance, it represents you're bringing the atom closer and closer. Okay. So if you're only here, just forget about this section. Imagine if you only bring the atoms up to this point, then only the last shell will split. And the other 2 shells will not split at all. They will be like rigid, no splitting. Making sense? Because you are not close enough so that the electrons in the underlying levels will start interacting with each other. They don't need to interact. The last shell will just interact and take care of everything. So the closer the atoms get, the more interactions occur and the more splitting will occur. Even starting from the last shell all the way down to the minimum shell, they can all split. And that is related to the compactness of a crystal. Remember, how many of you remember we calculated the volume density of atom, right? If the atoms are more closely packed, there is a chance that there will be more splitting in all the shells. If the atoms are sparse, like farther out, only the last shell will split and the other shells will be like, no, we don't care. Am I making sense? So see, all of these are related. And by the way, the same concept, it's nothing new, but the thing is they will start splitting after you bring them closer, even closer. Then the second shell will start splitting. If you bring them even closer, then the first shell starts splitting. So you have to bring them more and more close to each other. So make them more compact and jam-packed with each other. All right. So lattice concentration. So the lattice compactness has a role to play. Now, this is also a little bit involved slide. And if you listen to me and if my message makes sense to you, I'm sure once you read it, it will make sense. But if you don't, I mean, all you need to know is understand this concept. That's all. And if you have questions, please ask me. Because the textbook descriptions can be too complicated. They get into the weeds and oftentimes miss the point. At least as a student, when I was a student like you, I used to feel the same. And it was a struggle for me to basically get the full picture. So anyways, this is silicon. See, we are quickly getting into the point. Silicon Valley. So we're getting to the Silicon Valley right now. This is a silicon atom. We're getting more and more relevant to actual electronics. Silicon has 14 electrons in total. Okay. 2 and 8. So let me show you here. So 2 electrons and 8 electrons are distributed in the lower shells, and the other 4 are distributed in the outermost shell. So I mean, I'm just trying to show it here. 2 electrons here, 8 electrons here, and the other 4 are at the outermost shell, which is farther out from the other shells in energy, by the way. So you see, obviously, when we start bringing silicons together, so if this is a silicon, if there is another silicon, which shell will interact first? Folks? Of course, the outermost shell. And by the way, for silicon, that is more than enough. We don't have to, basically, in a silicon crystal, we don't compact them enough in a way that it becomes, it gets to a position where the lower shells start interacting. Just a funny point, side note again. Diamond is carbon, graphite is carbon. Like basically, carbon is carbon, obviously. All of these are carbon. But all on a sudden, diamond's property is unlike anything like coal, for example, right? What happens there? The chemical formula is basically the same. C, that's it. See, diamond happens when? Extremely high pressure, maybe the core of the earth or something like further down the ground. So if you make them more and more compact and jam-packed, see, all on a sudden, properties change. See, that's how impactful this compactness can become, because you see, even the electronic shells start interacting and the quantum levels change. So for silicon, the conventional silicon that we use for our stuff, we typically get only the last shell interactions. We don't have to deal with the internal interactions unless you artificially make it compact or do something about it, which I'm not getting into. Anyways, so this is what happens for silicon, specifically silicon, without any sidetracking, just silicon. Okay, and I'm going to give you the final message without going through the details. So the 4 shells of the 4 electrons that you have in the outermost shell of silicon, how many of you remember SPDF distribution from chemistry? How many? Some of you. Okay, it's okay. Don't worry. Even if you don't remember or if you haven't seen it, that's totally fine. I'm not going to get into chemistry here. All I want to tell you is, if you remember that S orbital could accommodate 2 electrons, P could accommodate 6, and so on. Okay, 10, 14. So S can only accommodate 2. So you had 4 electrons in the outermost shell. Every shell has SPDF, say, can have SPDF type orbital. So outermost shell has S orbital, P orbital, D orbital, blah, blah, blah. So it basically has just S and P based on the numbers. S can only accommodate 2 electrons. So what will happen to the other 2? The other 2 will go to the P orbital. And that's what you see. This is taken from textbook, by the way, exactly a screenshot from textbook. So 3S and 3P. 3 represents, it's the third shell. Third shell, for both cases, you have S and P. In the S orbital, you have 2 electrons. For the P orbital, you have 2 other electrons. Okay, that's how it is. And just all chemistry, no electrical engineering involved here. Okay. So that's how typically electrons are distributed in silicon, 2 and 2. Notice one thing. In a conventional single atom of silicon, 2 electrons will be in a lower energy level and 2 electrons will be in a higher energy level, slightly higher. So these 2 electrons will be happier because they have slightly less energy than the other 2. So there is an asymmetry in silicon. You see that? Only when the silicon is alone, just a silicon atom has some asymmetry in terms of energy. Okay, but here is what happens when you bring them together. This is equivalent interatomic distance. So basically, in a crystal, you get that much distance. That's what it represents. If you take a look at the crystal, silicon crystal, atoms are this much out, further, this much out from each other. What's happening here, folks? Can you tell me? I'm going to show you one thing. Okay, here, maybe I can use this. It's a little bit complicated, but I'm going to show you this here. What if it keeps splitting as much as the top level and bottom level start merging together? Okay, so same thing happened here, you see? So basically this was splitting and this was splitting, and there is a complicated situation here. But don't worry, we don't have to deal with these complications. Why not? Because naturally, what is the separation between 2 silicon atoms in silicon crystal? What is the separation? This is the separation. That's what A0 represents. Remember that. A0 represents, naturally, this is what you get. So let's see what we get naturally. And I'll get to that point later. So you have this type of splitting, and this is what you get naturally. So if I take this out and plot it on the side, you get a zone of energy here and a zone of energy here. And there is a zone which doesn't belong to S or P. Do you see that, folks? Am I making any sense at all? Okay. All right. Now, this zone, I'm going to get into the separation between the zones in a second, but let me show you some numbers, because you will see those numbers in the textbooks and you might be confused later on. So remember, S orbital can accommodate 2 electrons, P orbital can accommodate 6 electrons, and imagine you have n atoms, n uppercase n atoms in the system. So can I say I can accommodate 2n electrons in the S orbital and 6n electrons in the P orbital? Can I say that? And that's what you see here. 2n electrons can be accommodated here. Basically, you have 6n states, but you don't have that many electrons. You just have 2 electrons left. So essentially, you'll have 2n electrons in the S shell, 2n electrons in the P shell for a conventional simple silicon, which is just acting alone. N represents how many atoms are there. Will you be confused later on looking at it? No. Okay. So, but how many states were there? How many states? You had, why is it happening all the time? I don't know. Let's see. Okay. So you had 2n and 6n states. So a total of 8n states were available. 8n states were available. So after interaction, after this splitting, and we are just seeing what happens naturally, by the way. I'm just stating what happens naturally. Okay? This is not coming from math, by the way. So, okay, sure. We notice that you split it in a way that 4n states come here in the bottom portion. 4n states, meaning half. Out of the 8n states that you had with S and P together, 4 comes in this band, the 4 other goes to the other band. So it's almost even splitting. Does that make sense to you, folks? Now, how many electrons did you have, folks? 4 in the outermost shell. Or if you consider all the atoms, then 4n. How many states do you have in the bottom band, like this band? I haven't given it a name yet. I'll give it a name later on. But say band B and band A. How many states do you have in band B? 4n states. How many electrons do you need to accommodate? 4n. Naturally, will the electrons prefer going to the lower band or the higher band? I told you everything wants to go to lower energy. So all the 4 electrons go to the lower band. And they will be very happy because they are all the same now. In a standalone silicon, there was a chance that 2 electrons were happier, 2 were not so much. But here, because of crystal interaction, they find a situation where all 4 are equally happy. So they are basically, pure silicon is a really bad conductor. They don't want to give up their electrons because they're nice and happy. Why will I go to the other place? I'm happy. I have everything I need. My neighbors have exactly the same thing I need as me. So there is no asymmetry in pure silicon. Are you guys all with me so far? Okay. Now, remember that zone, this is EG, it's marked ECE, so it must be something important. So there is a band of energy. Let me just draw it here in a simple way. There is another band in energy. Both bands have quantum states. So you can have, kind of like you can buy property here or here. It's like available for sale for 2 electrons. Electron, come, buy a property here or buy a property here. However, there is a zone where there is no quantum state available. It's not for sale. Like, no, even if an electron tries to be there, it's not allowed by quantum mechanics. So this zone is called forbidden band. Remember that. This is a very important term. And by the way, forbidden energy band. It's a term. It's not, I'm not making it up. Okay. Forbidden band. And the ones that are on the top level, I'm going to show you why it is called so. The one in the top level, somehow you could do something to silicon that you can create some extra electrons in the top level. And the top level is kind of disjoint from the rest of silicon, and the silicon doesn't care what happens to that electron. Okay, just take it. Take it, do whatever you want with it. Okay, so those electrons are similar to what happens in metals. The electrons in the outermost shell is as if they don't care. So they just flow around freely. Similarly, if you could somehow create, and I'm not telling you yet how, but I will later on. If you could somehow create extra electron in that shell, which is just sitting there with some quantum states ready to grab, sure, then silicon can behave like a conductor. Otherwise, silicon is basically just an insulator. Pure silicon is just an insulator. 4-state, completely filled, no asymmetry, nobody wants to move anywhere. So it's basically an insulator. And this forbidden gap, this band gap, the separation between these two levels ensure that you could provide some energy to excite some electron to get to the other level, and that creates something interesting. Okay, but you cannot just do it all the time. Otherwise, it would be a metal. It's not a metal. It needs some inspiration to start behaving like a conductor. So that's why it's a semiconductor. And by the way, and I'll tell you how an insulator looks like. Let me just tell you now. What if in some materials, this band gap is so much, forget about some material. Imagine naturally, what if silicon's separation was here instead of this A0, what if it was here? You see that the band gap would have been much higher. So it would have taken more energy to go from here to there. That means it would have been very difficult for you to push anything to the upper layer to make it free. So that's an insulator. Basically, it's similar to semiconductors. Insulators are similar to semiconductors, but they have higher band gap. That's all. Super simple. Higher band gap, insulator. Moderate band gap, semiconductor. And typically for metals, and I'll show you that in a second. I don't want to go through all the cases. The band gap is basically non-existent for most metals. So basically they march together. Okay, imagine in this section, hypothetically, electrons can be here or there, or doesn't matter. They are all part of the same band, right? There is no band gap. You see that? There is no band gap. So for some reason, if our interatomic distance were here, if we could somehow do it, somehow create a silicon where the atomic separation in a crystal is here, then you have something interesting. No band gap. It's like a metal all the time. By the way, and that's how people use, like for material engineering, people tweak all of these things. If you could somehow create changes to the atomic structure, dramatic changes occur. Simply by changing your crystal distribution, you can make something into an insulator or semiconductor or a metal. You see? If I could somehow, if I had a magic wand that could change the separation between silicon atoms in a crystal, I could deal with a metal, I could have dealt with an insulator, I could have made into a semiconductor. But naturally, this is what we get. Natural separation is here, which is indicative of a semiconductor-like behavior. Does that make sense to you folks? All right. Let's move to the next one. All right. See, this is a special note. The sections following will be marked with begin and end, and they will not be part of any exam or anything. I just wanted to assure everybody. All right, when you read, don't be too lost into this. You don't even need to honestly review this after this. But I felt like spending 20 minutes or so now at this stage of your career will hopefully have more impact in your understanding, or possibly sparking interest to better understand the overall dynamics, then completely skipping it and getting to the point. Because I've been through this situation where, you know, things were skipped, so it was really confusing. Anyways, let's see. Chronic penny model is a concept that helps explain electronic behavior in a crystal in a simpler way. See, the same slide came back, and I stopped the previous lecture with this slide. I wanted to show you that this is where we're headed, and here we are. And I already explained what this thing is for a single atom. For multiple atoms, you have interaction, and eventually they all combine together to form energy barriers like this, which are more practical. Like there is no real barrier that is like as, you know, dramatic as this one, this square-shaped barrier. These are like approximation, mathematical approximation. But who cares? We could just approximate, just for the sake of math. We could just take it as an approximation and convert this real potential to square-shaped barrier. And that's what the chronic penny model will do. Chronic penny model takes the realistic potential of inside an atom in a crystal. So this is atom 1, 2, 3, 4, 5, many atoms side by side. Remember, in practice, it's 3D, by the way. You see, we are just looking at a 1D. So that's why it's a one-dimensional periodic potential function. Why is it periodic? See, the same thing coming back. It's like a sine wave. That's why it's a periodic potential. Making sense? And this is a chronic penny model because it's like a simplification of the actual thing. Are you guys all with me so far? What are we going to do? What? Oh, sorry. So what happened to that thing? All right. So when we try to understand the behavior of electron in a system, we always go back to what? Tell me now. Like, start being comfortable with this type of conversation. And again, one other thing that I'm trying to do here is trying to make you kind of ready or kind of prepare you as much as possible for a possible interview in semiconductor industry. So someone from semiconductor industry shouldn't feel like, oh, these guys have absolutely no idea about how semiconductor field works. Okay, so please start responding, and you can be wrong here. It's totally a safe place, so nobody's gonna judge anybody. All right, so please tell me, like, if I try to understand or find out how electrons will behave in a certain systems, which equation I will go back to, or will you go back to? There is a name, Schrodinger's equation. Okay, Schrodinger's equation describes the behavior of an electron at a given time at a given place. Time and space, both were there in there. Okay, so we just put in an electron, write Schrodinger's equation for different regions, and try to solve the equation, find a solution. When you find the solution, it gives you graphs. Honestly, it's just a mathematical tool. It gives you a graph. Wow, blah blah blah, and then you have to make sense of those graphs. And that's what we have been trying to do. Remember, there are two lobes at some point, and I told you electrons could be either here or there, both equally probable. And that kind of allude to the fact that there could be multiple states within a level. Okay, so it's a mathematical tool. So there will be a lot of mathematics. But then after the mathematics is over, you have some graphs to look at. You try to make sense of the graph. And that's exactly what we're going to do over the next few slides. So hear me out. This is a very complicated situation because instead of just one quantum well or one quantum barrier, which we dealt with in the previous slides, obviously not dealt with, basically we looked at in the previous slides. Here you have both. You have a valley, and basically you see you have a barrier, you have a well. You have a barrier, you have a well. You have both. It's a more complicated situation involving both situations. So to simplify the math, typically people use a theorem called Bloch's theorem, and that simplifies the work function. It says for periodic potential like this, the work function could be approximated in this form using an exponent. And we love exponents because exponents are easy to differentiate, easy to integrate. They're basically the same. Am I making sense, folks? All right. So I'm showing you this because you'll find it in the textbook. So what is Bloch's theorem? It's a simple theorem, mathematical theorem that helps you simplify psi x, which is the wave function, in an exponential form. Okay. And by the way, the second equation shows the case where you have both space and time. The first one is time independent. The second one is time dependent. That's all. Simple. Okay. All right. But we're going to go back to this time independent because we basically ignored the time dependent part for now. So, okay, what am I looking at here? See, different zones. There are zone 1, zone 2. But they're periodic. So if you just solve the Schrodinger's equation in two zones, here and there, you could just repeat that across the stack and you get the same solution. So you describe the Schrodinger's equation in zone 1, you get a form like this. You describe the same in zone 2, you get another form. So they look different because there are different, situations. One is a well, the other one is a barrier. So in one case, tunneling is involved, the other case, quantization is involved. So it's kind of completely obliterating all of this description. We're not even going to try to solve it. So apparently, people figured out a condition. So this is the condition. A condition that needs to hold to even have a solution, by the way. Otherwise, this cannot be solved. So basically, there are situations where it cannot have a solution. These equations cannot have a solution. So to make sure that you even have a solution, this condition must hold. And all of these details, how do you arrive at this condition? It's there in the Niemann book. I love that book, honestly. I mean, this is one of my most favorite books. Anyways, but you don't necessarily need to go through it. But if you want, there are a couple of students in the last time I offered who actually went through it, asked me questions. I'll be happy to go over and answer questions during my office hours. But again, I'm telling you, you don't have to, okay? So don't feel bad about it. So this is the condition that ensures that you will even have a solution in that equation, all right? And that condition comes with, by the way, if you take a simplistic representation of this term, which is p prime, you get this equation, which looks more manageable. Looks more manageable, okay? So just take a look at this equation. I guess still with me? All right. We might run out of time, but I'll stop in that case, in case we run out of time, but let's keep going and see whether we could make it. So for a free electron, first of all, this term could be ignored and you just have these two terms. Why? Let me explain. You see, there is a V0 here, which is a potential. For a free electron, you are not binding it with any kind of potential barrier or anything else. So potential is 0. So if you put V0 equals 0, which is here, your P dash becomes 0. That means this term is gone. So you have cos alpha equals cos K, which is this one. Am I making sense? So that's how we simplify the case for a free electron. And what I forgot to mention is you don't just have this equation. There is another simple equation, which is this thing. Just remember that. So if alpha equals K, which is the wave number, you just put it there. So you get an equation for wave number. And you plot the equation, which is parabolic. Again, I'm kind of skipping this because I'll get back to this soon enough. So this is called EK diagram, energy versus wave number diagram. And if you plot this equation, it comes out to be parabolic, simple parabolic equation. So apparently for a free electron, the EK diagram, energy versus wave number diagram, is a simple parabola. And we'll get back to the previous, get back to this later on. Let's get to the next slide. What if it's not a free electron, right? Which is more exciting, obviously. Then you have this side. Now, let's take the left-hand side and right-hand side separately. Let's consider left-hand side is a function of alpha A. Right-hand side is also a function. So we take these two functions. Okay? So to have this equation satisfied, we'll have to find a common zone geometrically, and we'll do it geometrically because it's very difficult to do it analytically. Take a look at cos A. Can anybody tell me what is the maximum value of cos theta? 1. What is the minimum value? -1. So any cos will have to be within -1 and +1. So you see, if you take this cos function, it will always be within -1 and +1. You see that? I'm setting a barrier here. Does that make sense, folks? Okay. So for the right-hand side, which is a cos function, the values can never be above 1 or never be below -1. So it has to be within this zone. That's a rule that I'm setting for myself. Okay. And take a look these other two sections. Just plot them. Just plot them. So if you plot the sine part, you get a wavy shape like this. If you plot the cos part, you get this simple sinusoidal wave like this. If you add them two together, are you guys still with me? Please don't give up. I mean, if you have given up, tell me, I'll get back to it in the next class. But, oh, the time has given up. Okay, it's fine. Let's not rush. We'll get back to this slide in the next slide. This is really interesting. Trust me. I find it really interesting. So we'll do it in the next class.